Hi, my name is Dennis Mitchell. I'm reading Carl Sagan's description of a subatomic particle called a neutrino. In his book Cosmos, Sagan states, "The sun glows faintly in neutrinos which, like photons, weigh nothing and travel at the speed of light. But neutrinos are not photons. They are not a kind of light. Matter is transparent to neutrinos. As I look up at the sun for a second, a billion neutrinos pass through my eyeball. If at night I look down at the ground, toward the place where the sun would be if the earth were not in the way, almost exactly the same number of solar neutrinos pass through my eyeball, pouring through an interposed earth which is as transparent to neutrinos as a pane of clear glass is to visible light." Interesting description, but I question his assertion that neutrinos weigh nothing. Even the glossary of Stephen Hawking's A Brief History of Time suggests that neutrinos may not have mass. Well, it hasn't been easy to learn about neutrinos. In fact, about 50 years before Cosmos was published, the existence of neutrinos was only inferred. It was in 1930 when a scientist named Wolfgang Pauli was studying nuclear decay. He noticed that a small amount of energy couldn't be accounted for. The deficit indicated the existence of a subatomic particle that no one knew about. When Pauli mentioned it to Enrico Fermi, Fermi came up with the Italian name neutrino, the little neutral one. Although little it may be, there sure are a lot of them. In fact, after the photon, which makes up light, the neutrino is the second most abundant particle in the universe. Therefore, in order to understand the universe, it certainly would make sense to study the neutrino. You might already know about one facility in northern Minnesota where neutrinos have been studied. It's the neutrino detector in the underground mine at Sudan, Minnesota. It's often referred to by the acronym MINOS. Well, there's now a newer and larger neutrino detector located to the northwest of Sudan along the Ash River. It's referred to by the acronym NOVA. Last November, I got a chance to visit the NOVA facility. It's located east of Highway 53 along St. Louis County Road 129, which is also known as the Ash River Trail. Although the facility is just outside of Voyageurs National Park, it's still situated in the same forested wilderness that makes up northern Minnesota. The formal name of the facility is the NOvA Far Detector, which distinguishes it from a near detector that's close to Chicago. At first sight, you may think that the NOVA facility is a factory, and the steady hum inside sure sounds like a factory, but it's really a giant research laboratory. And to explain how it got started and how it works, I met with Bill Miller, who brought experience to the NOVA project.
Must be Dennis.
I am.
Glad to meet you. I'm Bill Miller. I'm the lab manager at the NOVA site here.
Mr. Miller, pleasure to meet you. And you're the lab manager. Mm-hmm. Can you tell me a little bit about your background and how you came to this position?
Well, actually, I was the lab manager at the Sudan Underground Lab for over 25 years before we started this project. And they asked me to move up to Ash River and manage this while we built the next generation of neutrino detector.
Although I knew what Carl Sagan had to say about neutrinos, I was eager to ask Bill for a current definition.
So neutrinos, they're very, very small. They're on the order of a trillion thousand times smaller than an electron. So they have very little mass. In fact, when we first started MINOS, we were really trying to prove that neutrinos did have mass because it's so small, it's hard to get any kind of measurement.
Okay, so Carl Sagan was mistaken in suggesting that neutrinos are without mass. But it's not a mistake to say that neutrinos are without charge.
They also have no electronic charge, so they're not attracted to a positive or a negative charge. So they travel in a perfectly straight line. and 99.999% of the neutrinos that are made and all the stars in the universe just go straight through the Earth, come right out the other side, and never interact with anything at all.
In other words, neutrinos can travel like a ghost going through a wall. But another interesting aspect is that there are three types of neutrinos: the electron, the muon, and the tau neutrino. And what's really interesting is that neutrinos can change from one form to another. In other words, they oscillate. By the way, I was curious about what the four letters in NOVA stood for. Well, it turned out that the scientific habit of using Greek symbols was a clue. Maybe you could explain what NOVA stands for.
Well, it's a little bit tricky. NOVA stands for NUMI, off axis, because we're not on the neutrino beam axis, neutrino appearance experiment. Of course, then you have to say what is NUMI, because it's another acronym, and that stands for muon neutrino at the main injector. And so that was from the original experiment, Minos at Sedan.
All right, just one more acronym to learn. Minos stands for main, injector, neutrino, oscillation, search. The phrase main injector refers to a particle accelerator at Fermilab near Chicago. It is part of a process that sends neutrinos through the Earth to both Minos and NOVA. We'll get back to that later. But getting back to a perspective on the NOVA facility and its purpose, I wanted to know what scientists hope to learn from the NOVA experiment. So I went to the Department of Physics in Marshall Allworth Hall on the campus of the University of Minnesota Duluth. I got a chance to visit with Professor Alec Habig and asked him what he and other scientists hoped to learn at NOVA.
With NOVA, we're trying to see how the neutrinos change in their 800-odd kilometer trip from near Chicago to up, well, as far north as you can go in the U.S. and still be on a road. NOVA's built on the last road before you hit the Voyageurs National Park and then Canada. And we want to learn how the neutrinos change as they travel along, because like all particles, they're waves with quantum mechanics. And they're the fundamental particle that we know the least about because they're so slippery. And we're successfully shooting them right through Wisconsin, and they mostly don't care. That also means they go right through your detector and mostly don't care. And unless one stops and gets so incredibly unlucky as to belt some atom in your detector, you never know what went through. That makes them really hard to study.
Then it was time to ask the big question. Would NOVA answer any questions about the universe itself?
The one question about the universe that we think it might answer, and it's kind of really big and sweeping, but is why are we made of matter? We're pretty sure the universe started off with the Big Bang, just a pile of energy. It was very hot, very dense, and as that expanded and cooled, ordinary things formed, and now space is mostly empty except for stars and planets and things like that. But it's all matter. It's all regular matter. When you take energy and you make matter out of it, you get equal parts matter and antimatter. But then again, if you take the matter and the antimatter and you bring them together again, they wipe each other out and quite thoroughly. So if we started off as a bunch of energy, the universe, because it was so crammed together, expands, cools off, matter pops out, antimatter pops out. Give enough time, that matter and antimatter should swim back together, blow themselves up, and we should have a mostly empty universe. But that's not what we see. It's matter. And so something about matter and antimatter behave differently. The laws of physics as we know them say that for the most part, they behave identically, just flipped. So an electron is negatively charged and an anti-electron is positively charged, but otherwise they have the same mass, they do the same things, for example. Neutrinos might hold the key to how neutrinos and antineutrinos behave differently from each other, might hold the key to learning why matter and antimatter in general behave just differently enough that as the universe settled down and cooled and most of the matter and most of the antimatter do what they do and wiped out, we're left with matter. Enough matter to make us and galaxies and dark matter and planets, stars, everything else that we see, which is all, as far as we can tell, perfectly normal matter. So where did all the antimatter go? by shooting beams of neutrinos and then beams of antineutrinos and measuring how they change on their way between Fermilab and Ash River. That's the key we hope to get at.